Write down the IUPAC name for each of the following complexes, okay, and indicate the oxidation state, electronic configuration and coordination number. Also give the stereochemistry and magnetic moment of the complex. So greedy they are. It looks straight from our notes, but then, well, tell everything. There we are. Let us say everything. First of all, the IUPAC name of each of them. First one, let me write down potassium. And then brackets begin. So I'm going to write down a space, there's a blank, and then I'll write the further name. I have to list all the ligands in alphabetical order. So di aqua, di oxalato. This is oxalate, so dioxalato. Chromate 3. Why did I write chromate? It is chromium. And if this is anionic part, I must put suffix 8, so it is chromate. Oxidation number is 3. Well, it looks like, why? Oxalate is -2. The -2 into 2, -4. So this also should add up to +4 because water has no charge. Potassium is +1, so chromium has to be +3. That's why chromate 3. There is some water of crystallization also. This water of crystallization is simply written as -3 water. Please don't write it as aqua. Aqua means ligand. Water means water of crystallization, and that's the way we simply write it. The number followed by the word water with a dash. That's it, that's it. The first name. Let's write down the names first. Second name. What is this? CONS3 whole 5. This 5 should come here actually. Cl. So this is pentaamine chlorido cobalt 3. 1 and 2, 3. 3. Chloride. Lovely. That's it. That's it. Beautiful. Third one, CrCl3py whole thrice. This is trichlorido trispyridine. Organic ligands, usually instead of ditri, tetra, it is best to use prefixes as bis, tris, etc. Chromium. 3. There is no cation anion, it's a neutral coordination sphere. This is third. Fourth, I think I have some space here, I'll write down. CsFeCl4. This is cesium. Gap, and then tetrachloridoferrate 3. Why ferrate? Because iron is a part of anionic complex. That's why 8. Why 3? -4 charge on Cl atoms, +1 on cesium. Iron also has to be +3. Fifth part. K4MnCN6. Potassium. Hexacyanido C. Why C? Because sometimes people skip C because ambidentate ligand of cyanide is cyanido C. Manganate, and what is the oxidation number? +2. Manganate 2. So even if you have written potassium hexacyanido manganate 2, it's okay. But if you want to be very accurate, because cyanide is ambidentate, it is best to mention hexacyanido C, manganate 2. Right? These are the names. And yes, there are other gory details also. They're asking you oxidation state. So let me make a small table in which I will write down all these details for you. That becomes very nice, happy and pleasant. The oxidation state, and I believe this is oxidation state of central atom. Electronic configuration, coordination number, magnetic moment. We will write down everything. Fine. So let us begin with the oxidation state. The first one, oh, I just wrote here, I should not have written here. I'll just erase it off. Oxidation state. And electronic configuration. This is chromium plus 3. We already mentioned this while naming. Chromium is plus 3 here. Cobalt is plus 3 here. Chromium is again plus 3 here. Iron is plus 3. Fascinating. Out of 5, 4 of them are plus 3 complexes. Perfect. One job done, oxidation. Electronic configuration. Now chromium plus 3 is argon 3d3. Cobalt plus 3 is argon 3d6. You can count and check. Chromium back again to this argon 3d3. Iron plus 3 is argon 3d5. Very interesting. And manganese plus 2 is argon 3d5. So we have 3d3, 3d5 and 3d6. These 3 cases. They are expecting coordination number, stereochemistry, magnetic moment, everything. Well, stereo we will handle at the end. Let's now look at coordination number, which is easiest and very easily determined. 2 plus 2 plus 2. Why? Oxalate is a bidentate ligand, don't you forget. So 2 into 4 plus 2, 6. So coordination number is 6 in this case. Cobalt, 5 plus 1, 6. 3 plus 3, 6. In this case it is 4. And the last is again 6 cyanides. So very clear, coordination number is usually 6. But in fourth case it is 4 also. Now we need electronic configuration and magnetic moments. Now this is the most crucial portion. Let me draw a box diagram for you and show you that. Can we do that? Of course we can. But we would need space for the boxes. Let's have it. Now aqua and oxalate are all weak field ligands, let's not forget. And there's no space here. I'll just draw boxes here. Right? I'll extend this and draw boxes here. Let me just take first one. It is D3 configuration, right? 1, 2, 3, D3 configuration. And then we have coordination number 6. So we have D2, sp3 hybridization, no doubt. The geometry would be, of course, octahedral geometry. Magnetic moment. Now there are 3 unpaired electrons. I'm just solving one, nothing else. There are 3 unpaired electrons. There are 3 unpaired electrons. I get mu as root 3, 3 plus 2. It is root nn plus 2, which is root 15, which is approximately 3.9 Bohr magnetons. All right? Yeah. Do we have stereochemistry talks? Yeah, we can have that. What would they be? Well, you have 2 bidentate and 2 monodentate ligands. This sounds positively complicated. Yes, we are not worrying about water crystallization. That would not be our worry for stereoisomerism as such. How do we do this? Let me just tell you. If you look at question number 1, we have described other things, and now if you look at the stereoisomerism part, there are 2 bidentate and 2 monodentate ligands. The 2 monodentate ligands, aqua they could be trans, yes, or those aqua ligands could very well have been cis. Like this. And the moment you have them cis, this is also chiral. This is not chiral. So 1 is not chiral, 2 is chiral. If it is chiral, my dear, you also have a mirror image. Yes. So just make that mirror image. Lovely as it may sound. You have ox and you have ox and you have aqua and aqua sitting here. This is 3. So 2 and 3 are enantiomers. They are non-superimposable mirror images. And then you have this. These are the 3 stereoisomers of question number 1. Now let's take a look at the second part. What does it say? We have pentamine chlorido cobalt 2. Yeah, cobalt 3, sorry. If you look at this complex, now first of all, oxidation number of cobalt would be plus 3. How plus 3? This is, say if this cobalt is X, plus 5 into 0 minus 1 minus 2 into 1, which is 0. So X comes out to be plus 3. Just add up all the charges. Amine has 0 charge, each Cl atom has minus 1 charge, so cobalt adds up to plus 3. What about electronic configuration? That would be argon 3d6. If you draw a box diagram, 1, 2, 3, 4, 5, 6. This is ground state electronic configuration of cobalt. What about the coordination number? 5 plus 1, 6. So coordination number would be 6. Yes, very much. Stereochemistry and magnetic moment. Let's calculate the magnetic moment. This is ground state electronic configuration. And if we look at cobalt, amine is a reasonably decent field strength ligand. That means, would it become a low spin or high spin complex? It should become a low spin complex. 1, 2, 3, 4, 5, 6. What about the hybridization? Hybridization will be D2 sp3. Unpaired electrons, are they present? No. 0 unpaired electron. So spin only magnetic moment mu would be 0. What about stereoisomerism? Actually, you have 5 ligands which are identical and only 1 ligand which is different. Geometry is octahedral, yes, but it would not show any geometrical or optical isomerism simply because of its symmetrical shape and ligands. So no geometrical, no optical isomerism, only one structure, and that is the octahedral structure of this complex. That is the second part. Look at the third part now. Third part gets even more interesting. CrCl3py thrice. Oxidation number is plus 3. It is argon 3d3. Okay. Coordination number is 3 plus 3, 6. 3 plus 3, coordination number is 6 for this complex. Yes, very much. Any more information about stereochemistry magnetic moment? We can talk. 1, 2, 3. This is D3 configuration, my dear. So even if you have coordination number 6, even if you have D2 sp3 hybridization, it's very, very clear that you have 3 unpaired electrons. Number of unpaired electrons is 3. The spin only magnetic moment is root 3 into 3 plus 2, root 15, which is 3.9 something Bohr magneton. This is our spin only magnetic moment. Okay. What about the stereochemistry? Stereochemistry is the most fascinating one. How? Let me show you. I'll need space to draw, so I'll just remove this. Watch this. If you have a geometry which is based on an octahedron, okay, so what? No, there's something significant. If you have cobalt here, that's lovely. Well, you should have cobalt, that's fine. And there are 6 ligands attached. 3 of them are Cl, 3 of them are pyridine. Cl, Cl, Cl. Just look at this, and if in case you have Cl, Cl, Cl. Now can you see that these three chloride ions, yes, I can see them, and they are in a plane, they are very much in the plane indicated by the red square. And this plane actually passes through the central atom of cobalt. Yes, very much it does. And if the plane joining any three ligands passes through the central atom, then we attach a name that this is a mer isomer or meridional isomer. It's a stereoisomer, it's a geometrical isomer. You have pyridines here. If you join these three pyridines, you'll again get a plane which passes through the central atom, and if you join these three Cls, you get a plane which also passes through the central atom. If the plane joining any of the three ligands passes through the central atom, the three identical ligands passes through central atom, then we say it is a mer isomer. On the other hand, if I have pyridine like this, and in case I choose just to join a plane made by these three Cl atoms, oh my God, I do get a plane, but that plane passes, that plane is a plane which does not pass through the central atom. It is just one of the faces of the octahedron. It is just one of the faces of the octahedron. Where is octahedron? I'm just trying to show you the octahedron, that's it. This is the octahedron. And that is why this is called facial, or in shortcut FAC isomer. So you have FAC and MER, facial or meridional isomers, and two geometrical isomers are possible for this one. Two geometrical isomers. Any optical isomerism? No, both of them are achiral. Both of them are achiral. Achiral means not chiral. There is no optical isomerism associated, but yes, they are very much geometrical isomers. This is the third part. If you look at the fourth part, CsFeCl4, the complex part is FeCl4 minus. It contains ferric ions. Wow. And ferric is argon 3d5. Chloride is a very weak field ligand, and D5 itself is a beautiful configuration. As a consequence, you find that in the hybridization portion, this invariably happens to be a high spin complex, no pairing necessary, no pairing possible. The hybridization is sp3. Coordination number is 4. Please note, coordination number is 4. Hybridization in this case would be sp3, because these are the only orbitals, 4 orbitals which are available for accepting the donation. We have oxidation state, electronic configuration, coordination number. Now stereochemistry and magnetic moment. I have 5 unpaired electrons, so spin only magnetic moment will be root 5 into 5 plus 2, which is root 35, which is 5.9 something Bohr magneton. So we have the magnetic moment also. What about stereochemistry? There is no complexity here. It's a simple tetrahedral molecule, very symmetric. All the ligands are same, homoleptic complex. There is no geometrical or no optical isomerism which is exhibited in this case. And there comes the last and the fifth portion, K4MnCN6. If you look at this, manganese carries an oxidation number of +2. Coordination number is 6 because it is coordinating with 6 ligands. Yes, manganese ions are 3d5. It is a 3d5 complex. Cyanide ions are very much strong field ligands. So although this may be the ground state configuration, you find that electrons are pushed inside. What do you get? In complex, this is what you get. 1, 2, 3, 4, 5. And then you have D2sp3 hybridization. Although it's a low spin complex, my dear, still you are left with one unpaired electron, as you can see. So number of unpaired electrons is 1, and mu would be root 3, which is 1.732 Bohr magneton. Wow. What about stereochemistry? All 6 cyanide ions are identical, so there is no scope for geometrical or optical isomerism. Nonetheless, geometry is octahedral around manganese. This is the complete description as expected from us for these complexes. Fascinating question.